presentation, that is Aerothermodynamic Analysis of Innovative Hypersonic Deployable Re-Entry Capsule, presented by Professor Savino from the Naples Federico II University.
Sorry, Chairman, to interfere while they're fixing it up. I would like to give an information and a request. Please, all speakers, make sure that your presentations is available at the technical staff. You can check up with the desk, at the reception desk. Thank you.
Okay, thank you very much to the organizers for this invitation and for this opportunity to present some of the activities which are ongoing at the University of Naples in the field of hypersonics. I have prepared this slide just as a very short introduction to show what are the main activities in Naples in the field of hypersonic. They include theoretical and numerical research in aerodynamics and aerothermodynamics, experimental characterization of thermal protection materials. We have a small plasma wind tunnel where, as you can see in this picture, we can perform assessment and characterization of TPS. In this case, the picture you see is a sharp leading edge of UHTC, the zirconium diboride silicon carbide that was mentioned before in the presentation by Professor Cao of Cagliari. And we have also in progress some studies on winged re-entry vehicles and future spaceplanes, but my presentation now, today, will be focused on the last point, which is innovative re-entry capsules. And we will see some, in more detail, some of the points that have been previously introduced by our colleague Lionel Marraffa of ESA. So these are the main points of this presentation. We will discuss very shortly the main capabilities of these deployable aerobrakes for re-entry capsules. We will see some Aerothermodynamics emission analysis. We will discuss some feasible missions. And finally, the final point will be dedicated to some activities which are in progress in Naples, in our region, in Campania, that have been previously supported by the Italian Space Agency and now are under the umbrella of the European Space Agency that deal with the development of technology demonstrators for suborbital re-entry missions. Some of the previous speakers have provided some numbers about enthalpies, about heat fluxes. We have seen some numbers. I just would like to remember to those of you who are not or less familiar with hypersonic re-entry, that the main problem in hypersonic re-entry is the enormous energy of the vehicle that must be dissipated during the atmospheric re-entry. When we talk about re-entry from low Earth orbit, I have estimated that the re-entry energy is in the order of 150 times the enthalpy of fusion of iron, or if you prefer, 7 to 8 times greater than the explosive energy of a bomb. So the main problem in atmospheric re-entry is how this energy is dissipated and how much of this energy is transferred to the skin of the vehicle, reaching enormous levels of temperatures. And this is why in 50 years and over 50 years of re-entry of capsules and blood bodies, big progresses and big efforts have been provided to improve thermal protection systems technology. Now, the main point is that when the bomb energy is released, this happens in a few milliseconds. But during re-entry, one of the most important parameters is the time. So how steep is the re-entry, how long is the re-entry trajectory? So one of the most important parameters that we have to take into account is the so-called ballistic coefficient, which is the ratio between the mass of the vehicle and the exposed surface area. The idea to have a deployable re-entry capsule is in order to increase this area. So we have seen before, we have one big advantage, which is the very easy accommodation in a launch vehicle, but the possibility to fold, to deploy this umbrella before re-entry in order to reduce this ballistic coefficient and in order to convert this very high energy in a very long trajectory at high altitudes where the atmosphere is more rarefied, and in this way reducing the heat loads and the mechanical loads. So this is just to show how the ballistic parameter can change the re-entry trajectory of a typical re-entry capsule. And the main idea with deployable re-entry capsule is to keep lower this parameter in order to have a very long re-entry and to reach the biggest heat loads and mechanical loads at the highest altitudes, as you can see in this slide, with relatively lower mechanical loads and heat loads. So another advantage is, of course, the possibility to perform aerodynamic deorbit without any dedicated propulsive system, and this is safe for sure. And again, last but not least, another advantage is the possibility to strongly reduce the lifetime of satellites after the end of the mission in order to contrast the formation of space debris, which is one of the most important problems in space today. So coming back to the potential missions, we have been investigating, first of all, space mailing from the ISS, as was mentioned before by Marraffa from the European Space Agency. In this case, the capsule can be launched, can be stored in the space station, can be ejected from the space station, and when the shield is deployed, the deorbit happens. So this energy is gradually dissipated in a very long time before reaching the atmospheric entry interface and then finally landing to the landing site. Similar mission, but a little bit different, is an independent orbital scientific mission. In this case, the capsule performs a dedicated experiment in low Earth orbit, and after the experiment is recovered. Another possible application is for Earth observation, in the case of quick access to space into specific orbit. In this case, we are talking about very short missions where enormous number of data can be collected and recovered safe on ground. As I was mentioning before, some studies have been performed in order to look at the problem of the space debris mitigation. This is just a slide to show how different is the lifetime of a CubeSat. CubeSat are very small nanosatellites in the order of a few kilograms that typically must be recovered not more than 25 years. In this case, this is the maximum altitude that can be reached without any deployable system. With an aerobraking system, we can strongly increase the initial altitude of the CubeSat, and this is a very good advantage. For what concerns the deployable systems, in the Campania region, there is a project which has been funded by the region and that will be carried out in the next 3 years. That is looking at the development, study and development of an air-launchable nanosatellite with recovery capability. In this case, the main idea is to have this satellite which performs the mission in a low Earth orbit. After the mission, the aerobrake is deployed, and the capsule can be deorbited and controlled during the orbit trajectory. This is a slide that shows how the umbrella can be modulated in order to control the re-entry trajectory up to the final landing destination. These are some plot of the numerical prediction. We can see how many orbits are carried out during the deorbit maneuver. These are the computation of the final leg of the trajectory, where the capsule reaches the peak heat flux and the peak heat load. But what is important, as I mentioned in my introduction, is the possibility to reach sustainable heat flux and heat loads what is important is that these heat fluxes that can be, of course, computed by conventional CFD analysis. What is important is that these heat fluxes can be affordable by existing commercial materials. So we don't need very special technologies since the temperatures are relatively low in order to be sustained by, these are off-the-shelf materials that can be procured, that we have tested. The left sketch is in my plasma wind tunnel in a very short scale. The right one is a test that has been performed in the Scirocco with a larger model. But these tests have shown that the heat fluxes and the heat loads that can be sustained are affordable. As I mentioned before, there is a project that has been supported by the Italian Space Agency and now is under study by the European Space Agency, which is coordinated by the Aerospace Laboratory for Innovative Components, ALI, which is located in Naples. And the main target of this project is to develop a suborbital demonstrator of this technology. The idea is to place this model in the fairing, not in the fairing, sorry, in the interstage between the payload and the motor of the Maxus sounding rockets, which is one of the rockets which is typically utilized by the European Space Agency in coordination with the Swedish Space Corporation and the Aerospace German Research Center. This is typically dedicated to microgravity research, but there is the possibility to place one ejectable payload at the interstage so that in the ascent trajectory of this rocket, the capsule can be ejected after the altitude is in the order of 150 kilometers. So the capsule can perform an independent mission up to the final landing site, which is normally in the north of Sweden. Okay, so these are calculations, these are studies. In this case, since we are talking about suborbital reentry, as was mentioned by one of the previous speakers, not orbital, the energy is less, but in any case, the heat fluxes and heat loads are quite comparable, and some technologies can be tested. I see that the light is, so I try to accelerate my presentation. It's not important to go into details of the numerical activities that are ongoing. I just would like to conclude this presentation mentioning the parallel activities which are now ongoing by a group of my students in Naples, master and PhD students, that are studying these problems, and they intend to prepare a proposal to the European Space Agency for the next announcement of opportunities. This is a similar sounding rockets, not the biggest one that we have seen before, not the Maxus. The name is Rexus. That means that is much smaller rocket, and the rocket is launched twice a year from Kiruna in Sweden. This campaign is typically open to students coming from universities of Europe, and my students want to propose a similar project at the student level in order to make some experience. Of course, in this case, the trajectory is much with much less energy because the apogee is in the range of 80 kilometers. So if you can see from these requirements, their system will be much lighter, 5 kilograms, but most of the main ingredients are in the same concept. They are studying, they are doing numerical computations, they are doing preliminary analysis, and okay, they are also in preparation of some scaled models. This is a sub-scaled model that they have developed with 3D printers, and they intend to do also some aerodynamic tests in wind tunnels and to prepare this campaign for the next year. So this is the conclusion. We have investigated different possibilities for orbital reentry and for suborbital demonstrator. This technology, in our opinion, is an important technology for the future that gives the possibility to open to many possible applications. We have seen some applications, but also, for instance, interplanetary missions or re-entry from not low Earth orbit, but at higher energy, if the concept is successful, can be investigated. Okay, we have identified for the moment a number of materials that we have seen off the shelf, and okay, we hope that these results will be applied in future projects. Thank you very much for your attention.